So our today's keynote speaker is Professor Ravin Jugade, Professor of Analytical Chemistry at RTM Nagpur University, Nagpur. Dr. Ravin Manohar Jugade is a professor of analytical chemistry at Rashtrasandra Tukadoji Maharaj Nagpur University, Nagpur. He holds an MSc and a PhD in analytical chemistry and has qualified multiple examinations for lecturership. His research focuses on trace determination of metal ions using volatimetric techniques. He has successfully completed 5 research projects and currently serves as a principal investigator for a DST PERS project, which is worth of 11.42 crores, and the co-investigator of ANRF PIR project. With 120 research publications, 17 books, an H index of 31, and an I-10 index of 53. He has guided 11 PhD scholars, 1 postdoctoral fellow, and 60 MSc projects. Dr. Zugade has been honored with the Best Researcher Award and Best PG Teacher Award and serves as the director of the University Science Instrumentation Center and chairman of the Board of Studies in Chemistry in RTM Nagpur University. He is also a life member of several scientific societies and continues to make significant contributions in the field of analytical chemistry. Sir, I would now like to invite you to deliver a keynote address on the topic water detoxification using physically and chemically engineered Chitosan Biopolymer. Over to you, sir.
Thank you, Pratik, for the wonderful introduction. Uh, should I share the screen now?
Yes, sir.
Yeah. Is my screen visible to you?
Yes, sir, it is visible.
Thank you. Thank you, Professor Randive, for making me a part of this particular prestigious conference, the 4th International Student Conference on Medical Geology and Environmental Health. See, as the topic is based on the fundamental concept of this conference is a mixed crowd of medicine, geology, environment, physics, chemistry, everything put together in a basket. And that's why I have decided not to go with a very specific research type of a topic, but a general view of what we have been doing in our laboratory. So that I will be presenting in next 20 to 25 minutes. Pratik, how much time do you have? Do I have 20, 25 minutes?
So you have 30 minutes.
Okay. Thank you. Thank you, Pratik. Yeah. So I will be talking on water detoxification using physically and chemically engineered Chitosan biopolymer. I'm a strong believer of the fact that the success is a journey and not a destination. What we have been doing in our laboratory for last 10 years on a single molecule named as chitosan, and how that molecule has been utilized for removal of water toxicant, an important aspect of the environmental sciences. The need for fresh and good potable water is addressed by this particular molecule named as chitosan. I'll be talking about this particular molecule. So it starts with crustacean shell waste, and this is actually the source of this molecule chitosan. This crustacean waste comes from the crustacean animals, and then this on demineralization and deproteinization leads to a molecule called as chitin. This chitin is actually acetylated chitosan, and this chitin is deacetylated with leading to form with removal of that acetyl group. It leads to formation of what is called as a chitosan, that is a deacetylated chitin. So this can be carried out by 2 methods: the chemical method by using some acids and alkalis, or by the biological methods including the organic acids producing bacteria, the protease, and the chitin deacetylase. So this is a fundamental method of synthesis of chitosan from starting from the crustacean waste through chitin molecule. This chitosan is today the second largest available biopolymer after cellulose. So that is an important aspect because of the biopolymer nature. It is bioavailable and biocompatible in nature. Coming to very important aspects of chitosan, this chitosan has been reported in various fields and it finds applications in agriculture, food industry, pharma industry, cosmetics, paper industry, medical services, as well as water treatment. This is the area where our research group has been working for last 10 to 12 years. So if we search just the number of Scopus Index publications using a small, say, chitosan plus adsorption. So the application of chitosan in adsorption processes for removal of water toxicants, we will find that there is a consistently increasing trend over last 10, 12 years. And we are counting a small droplet into this big ocean. So why chitosan we have selected is chitosan has very important properties like hydrophobicity, biocompatibility, biodegradability, and non-toxicity. It is so non-toxic that it has been used as a supplement to our nutrition. It is a nutrient supplement. Apart from that, importantly, the chemical properties of chitosan involve two important functional groups, amino group and a hydroxyl group. These are reactive groups, and so these can be modified structurally and functionally as per our requirement so that we can lead to a particular molecule that will be useful for our applications. So specific modifications are possible in chitosan. Apart from that, we can develop composites with different types of chemical and physical modifications. And after use of this particular composite for water toxicant removal, that can be regenerated and reused. That gives an important greener dimension to this material. So these are the important properties of chitosan which attracted us leading to the research by using this particular biopolymer for the removal of water toxicants. So the water treatment technology mainly comprises of various steps, the primary water treatment technology, secondary treatment, tertiary treatment, followed by the quaternary treatment if as per requirement. Among them, this adsorption is an extremely important phenomena and the most common adsorbent which is used for the removal of or the common for multiple toxicants is the activated charcoal. But the specificity or selectivity of activated charcoal is not there. And as a result, we have been working with this chitosan as an adsorbent. Now, this native chitosan without any structural modification is a very good ligand because of the OH group and NH2 group present in it. So it can complexate various metal ions. Two models have been reported in the literature, like the bridge model, where any metal ion can be bridged between the two chitosan moieties, or the pendant type of interaction with the metal ions with some water molecules coordinating from the other side. So both of these models are reported in the literature. But if we find the problem is if we go to the adsorption capacities in milligram per gram, you will find that copper, cadmium, lead, nickel, all of them get absorbed or trapped into the chitosan matrix. But the adsorption capacities are very low, less than 20 milligrams per gram of chitosan. We have been working on this particular aspect that the adsorption capacity of this material should increase by structurally and functionally modifying this particular biopolymer. So what we are doing, we are basically chemical and physical modifications of this chitosan are being carried out. After that, the material is characterized through various instrumentation technique, including the FTIR, SEM, EDX, XRD, XRF, BET, and TGA, and the material is subjected to adsorption studies of the desired toxicants and then complete evaluation as an adsorbent by using some theoretical aspects like isotherm analysis, kinetics, thermodynamics, and response surface methodology. So this is what we are doing. And the targeted toxicants are the heavy metals, the dyes, the drug molecules which are acting as the emerging toxicants, you can say. And apart from that, some important anionic pollutants like phosphates, fluoride, and nitrates. So all these aspects our research group is working on. The chemical and physical modifications when we talk about are chemically modified chitosan can be obtained through various phenomena like cross-linking of chitosan chains, impregnation and grafting, synergistic aspect of these two, that is the cross-linking plus impregnation, composite formation, and we are having unique gamma irradiation facility in our university cobalt 60 source. So we are using gamma degradation of chitosan also for the modifications. So these are the chemical modifications and physical modifications leading to the preparation of chitosan or obtaining chitosan and its derivatives in the form of beads or microspheres, nanofibrous materials, magnetic beads, hydrogels or aerogels. So all these physical and chemical modifications are ultimately aiming at increasing the adsorption capacity towards the desired toxicant. That is our aim. One by one, I will just go through what are the modifications that we have done. So the first one is the cross-linking. There are two types of cross-linking agents possible for chitosan. One by using the multivalent ions, and second by using multifunctional organic compounds, leading to what is called as the ionic cross-linking and a covalent type of cross-linking. So both of these are possible. In ionic cross-linking, if we take a polyprotic acid, like say H2SO4 or H3PO4, then what happens is that the NH2 group of this chitosan is protonated by the acid, leading to formation of the NH3 positive ion, and the anionic component of this acid acts as a bridge between two chitosan chains. This leads to what is called as the ionic cross-linking of chitosan chains. Second type of cross-linking is the covalent cross-linking. Now, for covalent cross-linking, the commonly used material is the polyaldehydes, like glutaraldehyde, which acts as a bridge between the two. General chemistry of 11th standard taught me that if we have a NH2 group and if we treat it with some molecule containing CHO group, then it undergoes, say, dehydration, and it leads to formation of what is called as a bridge between the two chitosan moieties through the nitrogen atoms, and this type of cross-linking is formed. You will find that this is not the ionic but the covalent type of cross-linking is there. But the problem of this is that if we use glutaraldehyde in higher concentrations, the NH2 moiety is lost, which is a very important ligand for capturing of the metal ions especially. So this is a disadvantage of using glutaraldehyde as a cross-linking agent, because this nitrogen gets involved in the cross-linking and it is not available now for the chelation of the desired metal ions. So the better cross-linking agent than this is what's called as the epichlorohydrin molecule. Now this epichlorohydrin, you will find that it is cross-linking not through the nitrogen atoms, but through the OH groups. So you have now cross-linking through the CH2 OH groups, and as a result, the NH2 functionality is preserved. There can be a combination of both of them. The ionic plus covalent type of cross-linking is also reported in literature. If we use citric acid, you will find that acid is making NH3 positive, and as a result, this acid molecule is acting as a bridge, as an ionic bridge between these two. At the same time, there is a covalent cross-linking also by the same molecule, citric acid. So we can have ionic cross-linker, covalent cross-linker, and the dual cross-linker also. So what we have done now, if we see, this is a reported literature in 2009, this chitosan, native chitosan has been reported as an adsorbent for chromium 6 long back. Now what we have done is the adsorption capacity of this particular native chitosan is only 22 milligrams per gram towards chromium 6, an important, extremely important toxicant, which is carcinogenic in nature. We just carried out simple sulfate cross-link chitosan formation, which leads to formation of precipitate even if you put it in acid because of the cross-linking, and this leads to removal of chromium 6, and you can see the change in adsorption capacity increasing from 22 milligrams per gram to about 157 milligram per gram. very high increase in the adsorption capacity is observed. Similar type of work we carried out instead of sulfate. We used oxalate as a bridging agent. So using oxalic acid instead of sulfuric acid, the further increase in chromium 6 adsorption was found to be about 348 milligrams of chromium 6 adsorbed per gram of chitosan. So you will find that there is a continuous increase because of change in the bridging agents or the ionic bridges between the two. Apart from that, an interesting thing what we observed is this is a oxalate ion is a reducing agent. So it reduces that chromium which is from +6 to +3. So if you put the material with the adsorbed chromium for some time, you will find that the orange color has been changed to green color because of the reduction of chromium. Now that can be easily disposed because chromium 3 is not a toxicant at all. Coming to the metallic cross-linking, we have reported certain materials like stannic cross-link chitosan for the removal of arsenic. You will find that arsenic removal capacity of 266 milligrams per gram, whereas native chitosan, if we use for the removal of arsenic 3 ion, it was found to be only 1.83 milligram per gram. So here we have the ion exchange phenomena with H2ASO3 negative ion. So this is one phenomena which we have reported. Apart from that, this similar type of material, stannic crosslink chitin for the removal of fluoride ions. Now, fluoride is hardly removed from by using the native chitosan, but if we carry out certain incorporate certain multivalent metal like stannic ions into the matrix of the chitosan or chitin, we'll find that it has got a very strong adsorption tendency towards fluoride ions. So, and defluoridation can be carried out. Apart from now, cross-linking, there can be grafting of chitosan possible because of the functional groups NH2 and OH functional groups. Now, because of this, the fundamental chemistry knowledge tells me that this NH2 group can be amidated, can be epoxide opening. All these reactions can be carried out on NH2 group, and similar type of reactions can be carried out on OH group. So, large number of chemical modifications by using grafting and impregnation are possible because of these two important functional groups. So what we have done, we have carried out grafting on the NH2 group by using this diacetyl monoxime derivative of thiolated chitosan. And what we observed that the adsorption capacity towards chromium 6 has been further improved to 430 milligrams per gram. So starting from say 22 milligrams per gram, we have reached up to 430 milligrams per gram chromium removal capacity. And apart from that, an interesting component of this is again here also you will find that chromium getting reduced from chromium 6 to chromium 3. So highly toxic and carcinogenic material to non-carcinogenic material. Coming to the two combination of the two, synergistic effect of cross-linking plus impregnation. So we have reported ionic liquid that is aliquot 336 impregnated sulfate cross-link chitosan. So cross-linking with sulfate ions and impregnation of this aliquot 336 that leading to more number of ionic moieties into the matrix, thereby having very strong ionic interaction, leading to large increase in the chromium removal capacity. You can find native chitosan 22, sulfate cross-linked chitosan 157, and combination of sulfate cross-linked with further modification with impregnation by this aliquot 336, leading to 251 milligram per gram. And another aspect of phosphated chitosan with a quaternary ammonium compound impregnation, leading to 267 milligrams per gram. So very high improvement in the adsorption tendency towards chromium has been observed and reported in literature, reported by our research group. Coming to another aspect, that is a composite formation. Since last few years, we are finding that instead of carrying out the chemical modifications by functional or functional group in functional group modifications, it's always easy to form a composite. Like two types of composites we have reported: organic inorganic composites and organic organic composites. This can find two important aspects. One is a chitosan, which is a biopolymer, and second is the red mud, which is a waste material from the aluminum manufacturing industry coming from the bauxite ore. So it is actually a threat. Red mud is a threat to the nature, and chitosan is a biopolymer which is amply available. So we have a combination of these two clubbed together, forming microspheres or beads by mixing chitosan in acetic acid, and to that we have added that red mud solution in the form of suspension, and then dripping it into the cross-linking agent, and it leads to formation of very beautiful uh, the spherical microspheres, and these have been used for the removal of water toxicants, fluoride, chromate, and phosphate. You will find that all of them are environmentally important, and all of them can be removed by this combination of red mud and chitosan. Composite formation, we have reported certain materials for removal of fluoride like novel mesoporous chitosan zirconia ferrosulfuric oxide. This is a magnetic material for the removal of fluoride ion. Similarly, zirconia chitosan beads for the removal of fluoride ion, and highly efficient mesoporous aluminum magnetite alginate magnetic composite for defluoridation of water. Now, if you see this, you can see that in the fluoride is chitosan has almost negligible tendency to absorb fluoride. But if you form these type of composites, you will find that the fluoride absorption capacity is increasing successively with different types of combinations of the composites. So one metal oxides, and on the other side you have a biopolymer. The composite formation can also be organic type of thing. Like what we have reported is glutaraldehyde cross-linked chitosan alginate composite for organic dyes removal from aqueous solution. We have reported this type of what is called as a tweezer type of compound. So we have chitosan with alginate, and it is cross-linked, leading to removal of three important dyes: the brilliant green, methyl orange, and PB dye. Magnetic beads or microspheres have also been reported for the removal of reactive orange 19 dye with a very high absorption capacity of 196.3 milligrams per gram. An important aspect of this is it is actually magnetic hydrogel. So the removal of this hydrogel after the treatment becomes very easy. You can just add that microbe solution, you stir it for a certain time, that is get removed. So that in that magnetic material, this is actually the microspheres have been formed with combination of ferrous and ferric ions co-precipitation method. Recently, we have reported dual modification of chitosan with PLK. See, this is another aspect where geology and chemistry can work together. This partially lateralized chondrolite is actually it's a waste material along or from bauxite, and we have prepared bits of this material with chitosan, and we have used it for the removal of cyanide ions, an extremely toxic material. And we have reported two materials, chitosan PLK beads and chitosan PLK beads cross-linked with epichlorohydrin. Now, when we successfully modify these two, we'll find that the cyanide adsorption capacity, normally chitosan does not adsorb cyanide at all. But these beads have been found to remove cyanide 23.98 about 24 and 65 milligrams per gram with cross-linking with epichlorohydrin. Now, when you use a cross-linking agent, it leads to more porosity into the structure, because when water is removed from the structure, it leads to a porous nature and leading to a highly porous surface area you can see in the same image. Recently also, we have reported one more material, sequential modifications of chitosan biopolymer for enhanced confiscation of chromium 6 with chitosan oxalic acid. Along with that, we have added a biochar into the matrix. Again, as I have I have told that chromium 6 is only 22 milligrams per gram adsorbed on chitosan. But when you put biochar into it, sorry, oxalic acid cross-linked chitosan has an adsorption capacity of 348.3. And while when you put biochar into the matrix, because of the enhanced surface area, the further increase in the chromium adsorption capacity of 383.8 has been observed for chromium removal. We have reported various materials for dyes removal also. If you see this particular material, it is chitosan zinc oxide nanocomposite for removal of three important dyes: reactive blue 19, reactive orange 16, and Congo red dye. And the adsorption capacities are more than 100 milligrams per gram. So anything more than 100 milligrams per gram will be considered as a good adsorption capacity because of the strong ionic interactions, hydrogen bondings, and pi stacking between the various molecules. Recently, we have reported another aspect of the chitosan glutamic acid membrane for the multi-pollutant amputation. This material was reported for removal of four different classes of materials. You will find chromium 6, the metal ion, cyanide, another important ion, fluoride, another anionic species, and diclofenac, which is a diclofenac is an analgesic material. So this same material can be used, or same film, so membrane, can be used for removal of multiple toxicants and having diversified nature. Chromium 6, cyanide, and fluoride, and diclofenac, all of them have different type of molecular structures and molecularity. You will find this, the top, this is our film, and after treatment of, or after removal of chromium, the color, you can see that there is a complete change in color from almost white or colorless to yellow because of the removal or adsorption of chromium 6 moieties. Chitosan barbiturate acid, which is again a non-toxic acid, that has been used as a bridging agent leading to formation of hydrogel supersorbent for the sequestration of again chromium and cyanide ions. And you will find that we have reached to chromium adsorption capacity of 534.75 milligram per gram, almost highest in the literature today, by using some of the hydrogels. And cyanide adsorption capacity very high, 251. Almost, I haven't seen such a high adsorption tendency towards cyanide in the literature. One more material we have used, it's a ternary composite of chitosan, graphite, and polyvinyl alcohol. It's a magnetic hydrogel, again by using ferrosulfuric oxide, Fe3O4. And you will find that this has got a very high adsorption capacity of 196 milligrams per gram of reactive orange 16 dye. You can see there is a continuous decrease in the concentration of the dye when we move from left to right. In this particular picture, you can see there is a continuous decrease with time. These are the actual images of the dye concentration with time. This is a recent literature, recently reported material by our group in 2025 in multi-component adsorption of reactive dyes using iron linked alginate chitosan composite. Now it's a combination of two biopolymeric materials. One is a alginate, second is a chitosan. And what we have done is we have prepared 2% solutions of both of them, blended together, and then cross-linking agent glutaraldehyde and FeCl3 solution were mixed together, and this blend was added in the by using a syringe into it, leading to formation of microbeads, or what is called as the microspheres. And this was crushed and used as an adsorbent. And we have found that all the three in a individually also, and in a multi-component mixture also, all the three dyes were removed. And this is what we have done, is we have done some mathematical calculations involving the response surface methodology and what is the effect of presence of the other dyes on a particular dye. For example, when we change the dye, when we have a multi-component mixture, what is the effect of one dye on the adsorption tendency towards the other dye? So three dyes, reactive orange, reactive violet, and reactive blue. So three dyes were removed simultaneously from a mixture. The credit of this complete work goes to my research group in the Department of Chemistry of Rashtranath Puroji Maharaj Nagpur University. There are 17 students till date for last 10 to 12 years, and all of them have worked very hard in this particular area. Every student has got at least 5 to 10 publications with them, and with good fragrances they have given out very good output in the form of these publications. So credit of entire work goes to this team of these 17 students, from student number one from here to the encircling completely from these students who are working at present. So thank you very much for patiently listening. These are international collaborators, Dr. Saranand Pandey from South Korea, Dr. Rashid Billah from Morocco, Dr. Sarvanan, and Dr. Singh from India, the national collaborators. So thank you very much for patient listening, and thank you the organizers for giving me this opportunity. If you have any queries, feel free to ask. Thank you.
That's a wonderful presentation, Professor Zugade. Although we are work in the same university, but we rarely get a chance to know closely our works. Have you patented, sir, those films? They look very, very promising. And removal of chromium 6 to 500 mg per, that's too much. I mean, really wonderful work you are doing.
Yeah. So actually, sir, these were published earlier because we know that in university, the students are more interested in getting publications first.
Yes.
So patenting, we haven't done. Only one patent I have filed recently. That is the area where I'm lagging. With 120 publications, but hardly any patent.
No worries, sir. This knowledge should be shared, and that's what you are doing. So publications, fantastic, wonderful. So definitely students should come forward and ask their questions if they have any.
I now invite questions from the participants. If anybody wants to ask, interact with sir, they can put their questions in the chat box. Any questions from anyone?
Yes.
Any comments from
Uh,
our sessions? Yes,
Yes,
please.
Ariadne, ma'am.
Yes, hello. Congratulations, Professor Ravin Jugade. This is an excellent work and very, very interesting. I would like to ask you if you have tried to expand and upscale from the laboratory scale to actual applications, maybe
yeah.
with mesoscale experiments.
Uh, Actually, these, if we see this chromium 6 and fluoride actually we have worked on. Because we get fluoride, there are certain areas in the central India region where there are the fluoride is a common problem, because people many times they mainly depend on groundwater, and mainly the borewell water. So whenever there is a borewell type of problem, the chromium, sorry, the fluoride is there. So we have actually in one of our publications, what we have done is we have suggested a tea bag type of model, madam. Uh, if we have a material which is capable of taking up fluoride very fastly, then you can just put it in a container containing water, say borewell water or well water, which is fluoride rich, and you just move a tea bag like of thing through this, and the fluoride gets removed, and the concentration of fluoride in the water container decreases very rapidly. That is an area where we have done some work, upscaling to not for industry level, but for a domestic level, we can work with.
Thank you. Very, very interesting.
Sir, we do have a question in the chat box. Chitosan usually degrades in water. Then how could we use it, use to purify directly into the river water?
Yeah, it's not possible to work with in a river water, because river water, the conditions will be entirely different. This is what I'm talking about, is a treatment of wastewater. If we are discharging certain chromium species into wastewater, into the water bodies, before discharging, we can treat it. Just like the activated charcoal technology is used as an adsorbent, we can use this for selective adsorption of a particular species.
Thank you, sir. Do we have any other questions? I think there is a question, sir.
Yes.
Do we have activation of charcoal technique in RTMNU or in any other area that do you know?
Yeah, activation of charcoal can be carried out. That is not a problem at all, because see, there is no specific. There are multiple methods. Chemically, you can activate charcoal by using certain reagents. Okay, so say phosphoric acid activation, or there are multiple ways of carrying out activation. Ultimately, the aim is to enhance the surface area. That can be done. There
Thank
is
you,
no
sir.
specific technology for it, or a facility.
We have one more question, sir. What are the regeneration and reuse capabilities of the engineered chitosan material, and how do those affect long-term operations?
Yes. We cycles. Normally, what we repair using certain agents. For example, if we are carrying out fluoridation, so fluoride is getting trapped. So now we can treat it with simple NaCl, so that if we increase the concentration of chloride ions, there is an ion exchange taking place. So the material is now regenerated, can be reused again for defluoridation. So normally we test it for multiple cycles. So some of the materials, they sustain for 3 or 4 cycles. Some of the materials can be regenerated and reused to up to 10 or 11 cycles also, with a marginal loss in their adsorption capacities. Say for 90%, suppose it is adsorbing in the first cycle, it goes to about 85 or 84% in the 3-4 cycles. So regeneration we normally carry out. Not possible for the dyes, but for heavy metal ions, for we are doing it regularly.
Thank you, sir. Do we have the question? We can now start with the sessions. I would like to thank Professor Ravin Jugade, sir, on behalf of the entire organizing committee. Sir, it was a wonderful lecture, and I'm very sure that our participants have learned quite new things and new domains of the remediation. Thank you so much, sir.
Thank you very much, sir. Thank you.
Taking